All right, ladies and gentlemen, I want to start with the interpretation of the result after you have created your entire regression model. This model will have data information related to, several factors, several information. For example, the previous time we looked at the dependent variable being the Burkutijin betas. We estimated it using OLS, one with the intercept, one without the intercept. And then the generalized linear model. We looked at different stargazer commands for generating different models. Some of the results you'll be getting include standard error. That will tell you the level of accuracy of the coefficient. If you have the standard error, okay, and it's lower, it means that the coefficients are going to be, better. They are going to be much, much more accurate. Remember that the estimate divided by the standard error will give you the t-value. Okay, the estimate divided by the standard error will give you the t-value. This is something that you would have already seen in the regression itself, both in the simple regression and then in the multiple regression. You would have seen that yourself. So when you run it, it will give you that perspective. So let me just see if I could show you. But you've seen it before, though. If I could show you in the R. In the R. Hopefully you could see that R. So in this R, the estimate divided by the standard error, okay, will give you the t-value. Divided by the standard error will give you the t-value. And when the t-value is read on the table, you can get to the probability value. So these are the things you're going to find. You will also note that the p-value will tell you for each independent feature, there is a null hypothesis and an alternative hypothesis. The p-value will tell you. When the p-value is less than 5%, it means that the coefficient is significant. But I'll come back to that. And from this, you can generate confidence interval, which tells you the range in which your coefficients are likely to fall within a likelihood of 95%. So there are several ways in which you can actually generate these results. All right. So sometimes you have to drop insignificant independent variables and create a new model. Okay. So we're going to look at some few questions related to this regression. And the first question is, which independent variables are statistically significant? Which independent variables, the coefficient of which independent variables are statistically significant? Now, how do you do that? You have to use the p-value. You see, the p-value is the error that you make in conducting a hypothesis regarding the importance of an independent variable. So the p-value is the actual error. The alpha is the expected error. So you have to use the p-value to check if the coefficient of an independent variable is significant or is not significant. If the p-value, okay, is less than 5%, it means that the coefficient is statistically significant. So let's go and check each one of the p-values of the independent variables that we have. Check the p-values. Which of these independent, ignore the intercept for now, which of these independent variables have got a p-value less than or equal to 5% for it to be statistically significant? Which ones? Look at the price. Okay, the p-value for the price is 5.3%. So based on that, it's not statistically significant at 5% level. But then the significant cause will guide you to know some other thing. Okay, if you have a p-value with a star, Let's start with triple star. Triple star means that that independent variable is significant at 0.1%. Double star means that the independent variable is significant at 1%. One star means the independent variable is significant at 5%. And a dot means that it's significant at 10% and not 5%. So you can see that price is not significant at 5%, but significant at 10%. What do you think the complement price is? Because it has a 2 star, and again, check the value of the p-value. It is significant at 1%. Because if you should round this thing, it will be 0.0001, 0.01, okay, which is 1%, significant at 1%, but not at 0.1%. If you look at M, the income of the people, the p-value of this income clearly shows that it is 20.3%, which means is way above 5%, even above 10%. And that is why it doesn't have any dot or star. So it means that the coefficient of income is 0.98. It is insignificant in determining the quantity of gene bitters. Location urban is 18.6%, is insignificant. Occupation teaching is significant at 0.1%. In fact, all the rest are significant at 0.1%. So the p-value is very useful because it can tell you individually whether a particular independent variable has a statistically significant effect on the dependent variable. And the significant codes will also guide you in determining it. That is partial significance. That is not joint significance, because that leaves us with the next question. Are the coefficients jointly significant? How do you determine if the coefficients are jointly significant? You determine if the coefficients are jointly significant by using the F statistic and its p-value. Now, the F statistic here is 329.1. Okay, that's the F statistic, and the p-value is 2.2 E minus 16. Basically, what this is that there are 16 zeros before the 2. So it means that there are 0.15 zeros, then 2, which is approximately 0. So the p-value is approximately 0. And if the p-value is less than 5%, and in this case, it's approximately 0, what does that mean? It means that the coefficient put together jointly, statistically, influence the dependent variable put together. So some of the independent variables may not individually be significant, but when you put all of them together, they are significant. That's a united, front. So we can test for the partial significance, which is individual, and then we can also look at the joint significance, which is the overall. So this is one of the ways you can determine the accuracy of a regression. Now, let's go to how to interpret regression coefficient. Interpretation of regression coefficient. Now, the independent variables, some of them are static variables, which means they are dummy variables. Others are continuous variables, or they are numerical variables. The numerical variables means that they are dynamic. And if they are dynamic, what it means is that if you change them by a unit, at least within a year, the dependent variable is going to change by a certain amount. So the dynamic variables or the numerical variables can change. Let's take some of them. Okay. Let's go back to the story and see how we will interpret some of these independent variables. Let's start with price. The coefficient of this independent variable price is -3.15. R calls it the estimate. Excel calls it the coefficient. The negative 3.15 is the coefficient. How do you interpret it? This is how you do it. Because regression is an average measure, you start with something like on average. So you say on average, given the price of gin, on average, because you are interpreting price, you don't have to include price. Given the complement price of gin, which is a C, the income of the people, which is a M, the location of the shop, the occupation of the people, and the religion of the people, a 1 unit increase in the price of gin, reduces the quantity demanded of gin by 3.15 units. A 1 unit increase in the price of gin reduces. Why did I say reduces? Because of the negative 3. The 3 has got a negative. So because it's a negative, we say it reduces. So it reduces the quantity demanded of gin bitters by 3.15 units. Note that I did not say it decreases it by 3.15%. I did not use percentage. I did not use dollars. I did not use cedis. I just a 1 unit increase in the price cuts the quantity demanded by 3.15 units. So just keep the word at units, because sometimes once you bring percentages and things, you got to be sure that you have the logs taken, the logarithms taken before you can interpret things in percentages and other things. Okay, so that is how you interpret it on average. Look at the coefficient of complement price. It is negative 0.11. How do you interpret that? Of course, the price, when you have interpreted it in real papers, you can now add and say that, and this is significant at 10%, which we have already established, looking at a dot. Complement price, on average, given the price of gin, the income of the people, okay, and the location of the shop, as well as the occupation and religion of the people. A 1 unit increase in the price, in the complement price of gin, will reduce the quantity demanded of gin by 0.11 units. Now remember that even though there are 2 levels of occupation, I just put them together and say given occupation. Even though there are 3 levels, 3 levels of religion, I just put them together and say given religion. So you don't have to say given religion Christian and then religion Muslim or religion Buddhist. You don't need to do that. That's how you interpret this complement price. Remember, we are changing it. We are increasing or decreasing. That's why we said a 1 unit increase in the complement price of gin will reduce the quantity demand of gin by 0.11 unit. And this is significant at 1%. The same way you can interpret the income of the people. That's also numerical variable. So you say that on average, given the price and complement price of gin, location of the shop, and occupation and religion of the people, a 1 unit increase in the income of the people reduce the quantity demanded of gin bitters by 0.98 units. And this is, however, not significant at all. And that is how you will interpret the coefficient of income. What about some of the dummy variables? Let's take occupation. Okay. The coefficient of occupation is negative 19.43. Remember, Giving the 3 stars means that it's significant at 0.1%. How do you interpret that? How do you go about it? Well, again, you start with an average, given the price and complement price of gin, income of the people, location of the shop, and religion of the people. Quantity demanded is predicted or expected to be 19.43 units less if the people are teachers than traders. Why did I use than traders? Sorry, if the people are teachers than fishers. Okay, if the people are teachers than fishers. Why did I use fishers? I use fishers because fishing is the reference category. You see, the reference category is not documented here. Because anytime you mention teaching, you are mentioning teaching in reference to fishing. The same way, anytime you mention trading, you are mentioning trading in reference to fishing. And so you are comparing teachers and fishers. But watch it, because it's a dummy variable, we made sure that we were not increasing it, because this is dummy, it's categorical. So we indicated that quantity demanded is predicted to be 19.43 units less. Why less? Because of the negative. If the people are teachers than fishers, that is a dummy variable interpretation. You will not say that 1 unit increase in teaching. No, teaching occupation doesn't increase. The last one, let's interpret the coefficient of Muslim. Okay. Or let's interpret the coefficient, Muslim. Muslim is negative 23.01. How do you interpret it? You cannot include any of the religions because you are interpreting one of them. So you say that on average, given the price and complement price of gin, the income of the people, location of the shop, and occupation of the people, quantity demanded is predicted or expected to be 23.01 units less. I'm sure you know why it's less, because of the negative sign. Less if the people are Muslims, okay, because you know, if the people are Muslims, than what? Than Buddhist. Why Buddhist? Buddhist because Buddhism is the 3rd level of religion, which is not here. But from the story, you should remember and know what it is. Okay, so that is a reference category. Because it's a reference category, you explain everything in reference to that. So try and meet together and try and form some of your interpretation, because interpretation is critical when you are doing a regression. You got to be able to interpret all dummy variables as well as all numerical variables. Okay. Interpretation helps you to be able to make all the important points. And of course, when you look at the slides, you'll be able to appreciate some of the interpretations. Okay. Now, let's look at the fitness of the regression model. Another thing you should know, which would determine the accuracy of the model you have, is the R-square. There's another one called adjusted R-square. But first, let's understand the R-square. The R-square is a percentage of the total variability in the dependent variable. That is explained by the entire regression line. It tells you how good or bad the model, the entire regression model you have formulated is from the baseline model, okay, if there's any baseline model at all. So the R-square tells you, it's called the coefficient of determination. It tells you that it's not a statistical test, to be honest, like the F test or T test, but it is telling you together how much percentage explanatory power do the independent variables together have on the dependent variable. How much explanatory power? So the R-square is a very, very important measure of reliability or the fitness of the regression model. There is even the adjusted R square. That penalizes you for including irrelevant variables in the R square. So suppose that you have some 8 variables and then you want to include 10 variables. And so you just collect any variable to include. And it is known to the model that that variable doesn't contribute anything significant. That variable, if once it's in the model, it will increase the R square. But adjusted R square will penalize you for including such an irrelevant variable. The adjusted R square is always equal to the R square or is less than that. Okay. So the adjusted R bar square is always less or equal to the R square. When will it be equal to? It will be equal to the R square when all the independent variables are relevant. But when some of the independent variables are not relevant, whilst the R square can maintain its value of say 0.9, the adjusted R square will bring the whole thing down to say 0.78. Which means that adjusted R square is giving you the impression that there are some irrelevant variables in the model. Isn't that beautiful? Isn't that beautiful? Because it's a very powerful concept in the normal regression analysis. Okay. So let's look at our data. Is our regression model well fit? Is it fit? One way to do that is to check the R square in the model. So I'm going to go back to the model and I want us to check the R square. That is down here. The R square, we call it in R, it's called multiple R square. And of course, the adjusted is also here. And like you can see, the adjusted is slightly, lower than the R square, just as we indicated. All right. So what is the value of R square? Basically, it's 99%. What does that mean? It means that 99% of the variation in the independent variable is explained by the dependent variable, which in this case is the gem betas. 99% of the variability. So it means that it's only a small percentage of variability that cannot be explained by the R. That cannot be explained by the R square. So when is an R square good and when is it bad? This has been a big question for a lot of econometricians and others. Now, first of all, understand that both the R square, the adjusted R square, guide you in telling you the power of the model. Okay, and both of them are between 0 and 1. A higher value generally means that the model is better. A lower value means the model is bad. Okay. Our model. Is it better? Or is it not? How do you know whether the model is better? Well, one of my analysis shows that if the R square is greater than 50%, then the model is fit. If the R square is bigger than 50%, then the model is fit. And you want to check Hair Black et al. 2005 and subsequent edition. You will see that they make this point also explicit. So it's very important to ensure 99% of the variation in the quantity demanded of gene better explain all of the 99% of the variability is explained by the independent variables. So that is how you interpret the R square. The R square is not the only measure of the fitness of the regression model. Let me just take you back. To determine the fitness of the regression model, you can also use other measures like the MSE, the mean squared error. is the average of the squared errors. The average squared difference between the estimated values and the actual values. That is the mean squared error. We can use that. We can calculate the mean squared error for our model. Should I? The mean squared error, yes. This is how you calculate it. You take the mean of the residuals. Now remember the residuals, which is residual square, is inside the gene multi. Is inside it. So the mean squared error is the mean into bracket the gene multi dollar residual square. Okay, and this can be used to predict the accuracy of the model. It is 10.1. And it is positive, it's good. Okay, so again, it shows that the errors are not that significant. You can also even have the root mean squared error. Instead of simply taking the average, you can take the square root of that mean squared error to get the root mean squared error. This will tell you the metric. See, it doesn't matter whether you are using yards, dollars, numbers, the metric will be kept in the same unit as the dependent variable if you use the root mean square. So, and the other advantage of the root mean square is that if you want to compare different regression models, root mean square is a better choice than the R square. All of these are used to tell the accuracy of the model. Okay, let's look at the next thing that we can use to test the accuracy of the model. By the way, the root mean square, this is a formula for it. So mean square, and just bring the word root bracket. And at the end, you write root. Okay. Now, there is another way you can estimate another one, and that is the average absolute difference. The average absolute difference requires that you install a package called library metrics. Install the package, but do it in such a way that it's not going to cause any problem. It's not going to cause any challenge. The minimum absolute difference between the predicted is a difference between the predicted and observed. Now, when you calculate it, when you run it, you're going to get this value. Okay. And normally, a lower value is better. It shows that the model is fit. And looking at our own, we can predict the quantity demanded with an average error of just 2.789. So it means that we didn't make errors much on average. Okay. But here's a point to note. The root mean square is always greater, when it's always greater than the mean absolute error. It is because we notice that the root mean squared error will punish outliers more. So if there are outliers in the model, okay, your root mean squared error, will be bigger because they penalize the outliers. So they will punish you for having outliers in the model by increasing the root mean squared error. So if you have outliers in the model, it might make sense to use the MIRE. The next thing, okay, which is a mean, what do you call it? The average absolute difference. The average absolute difference, we call it the ABS. Okay, the mean of that is calculated as a difference between the predicted and the actual. And again, all of these are to handle some portions of errors. Okay, so in short, the errors here are minimal, generally speaking. So look at our data now, and we've been able to now look at all possible factors that can be used to make it accurate. What is the next thing to do? Well, the next thing to recognize is an important thing, actually, specifying the model. So regression models must be specified. You can have a Cobb-Douglas production function constant elasticity of substitution production function. You can have a Leontief, log normal, and several other models. How do you specify the model? Well, looking at the information here, you can use that and the beta parameters to formulate the model using the independent variable names. How do you do that? What you do is you write the dependent variable, which in this case is K. You bring a beta naught to represent the intercept. You write plus beta 1, the acronym name for the first independent variable. Beta 2 times the second independent variable. Beta 3 times the third. Beta 4 times the fourth, and then on and on and on. Specifying the model means that you need to also have the error term at the end. A model, a regression model without the error term at the end is not a properly specified model. Take note. All right. After you specify the model, you can now write the estimated regression equation. The estimated regression equation simply means replacing the beta parameters with their actual numbers in the table. So beta parameters, all of them will have to be changed and replaced with the numbers. How do you get the numbers? Go up to the model, everything under the estimate, make up the numbers. Some are negative, some are positive, so you take that into consideration when you are writing the numbers. So you write it like this. K equals to 280, which is an intercept, minus 3.15 price. So it's a betas, as you can see at the top here, it's a betas you are changing. Okay. Always, whenever you're writing a paper, remember to comment on your model. Okay? Give some practical advice, give managerial advice, policy prescriptions, and business insight on the results that you get. So you're not just calculating things and leaving them on, you're calculating and making sense of them and then using them even for prediction. Once the model has been built, estimated, and validated, remember that. That's when you use the R squared, adjusted R squared, the mean square, the root mean square, and all of those things. Once you validated it, we can now use it to predict the quantity of demanded of gene betas in our test data. Now, if the dependent variable is in logarithm, after making your prediction, you got to transform this value from log scale back to the original scale for easy interpretation. Okay. So it's very, in other words, when the values are, some of the values are logarithms, the way you interpret them is different from when they are not logarithms. Okay, so let's look at some prediction questions. Let's compare the predicted quantity demanded for gene betas. So we are looking for the Q, the quantity demanded for gene betas, that was made by some Muslim traders in an urban town. Muslim traders in an urban town. With that, let's compare it with that of the quantity demanded of gene betas made by some Buddhist fishers in a rural area. And in both cases, okay, the gene betas cost 15 Ghana cedis. Complement price is 15 Ghana. Average income is 20 Ghana. What is driving the difference? What is driving the difference? Now, how do you handle that? Well, the first thing you want to do is to write the estimated equation. Okay, so this is estimated equation. I decided to use the other data set for this, the one that was meant for the what do you call it, the coded data. Okay, so this is a price, and that C is the complement price. Okay. So that was a price, that's a complement price. You have the income here, the location urban, occupation teaching, occupation trading, religion Christian, religion Muslim. You have all of them there. So you have your regression. Now the question says this. compare the predicted quantity demanded of gene bitters that was made by some Muslim traders in an urban town. So let's look at it. They are Muslim traders and they are in an urban town. Remember that the price is 15, complement price is 15, and the average income is 20. So no big deal. This must be replaced. So when you go to the model, okay, this is the price. The price here will be 15. So you write negative 3.16 into bracket 15. And then the complement price is 15. So you write negative 0.211 into bracket 5. And then you do the same thing for this. Wherever you see the letter, change it. Wherever you see the letter, you change it. Wherever you see the letter, you change it. Yeah, okay. So that's quite easy for the numerical variables, because when it comes to the dummy variables, watch what you were told. You were told that they are Muslim traders in an urban town. So urban. Let's take the urban first. So LU is urban, and you have been told that the people are in an urban area. So as a dummy, to be given a value of 0 or 1. 1 meaning that it is urban, 0 meaning that it is not urban. 0. And so you will replace this LU with a number 1 because this is LU urban. So that is 1. Then you were told that they are Muslim traders. If they are Muslim traders, this one here is representing occupation teaching. That's teachers. Okay. So, but these people are not teachers, they are traders. So OT will be given a value of what? 0. And OTR, which is trading, will be given a value of what? 1. Got it? Okay. And then religion. You remember it said that the people are Muslim traders, Muslim. Okay. So the religion is what? Muslim. And so wherever you see religion Christian, will be given a value of what? 0. And wherever you see religion Muslim, will be given a value of 1. Once you have assigned these things, now each of the letters have got numbers, like you see down here. Okay. So you see the 1, 0, 1. And then you can now simplify it and you get a certain value. Maybe similar to what I have here. Not too much difference though. Once you get this value will tell you that this is the predicted quantity demanded. This is how much quantity will be demanded if all these are at play. Okay, so that is the first scenario. Let's look at the second scenario. The second scenario is that you are comparing this thing with that of the quantity demanded made by some Buddhist fishers in the rural area. So the religion has changed. The occupation has changed from trading to fishing. The location has changed from urban to rural. How do you plant this? Okay. So the same thing, write the equation. This is the equation. And remember that price and complement price were both 15, 15. Okay. You fill in the values of the numerical variables. Then LU, okay, location urban. Is it going to be 1 or 0? Remember, these are Buddhist fishers in a rural town, in a rural area. So because it's rural, urban here will be 0. They are Buddhist fishers. So occupation teaching will be what? 0. Occupation trading will be what? 0. They are Buddhist. So religion Christian will be what? 0. Religion Muslim will be what? 0. So that gives you the filling gaps. Once you have filled everything in, you now have this something similar to this value. Okay. If you check carefully, you might not get exactly the same, because sometimes I deliberately put up wrong values there so that you can work it and not go and pick this one. So when you do that, you now have, the two situations. Which one is more? The first scenario gave us 136.79. The second gave us 211.62, which means the second scenario where there are Buddhist fishers in a rural area, That one is better. Okay. That second scenario is 74.83 quantity units better than the first scenario. What is causing the difference? Well, we saw it. The difference is that we had the location. One was urban, the other was rural. So that was causing the difference. Occupation. One was traders, the other was fishers. Okay. So you compare that one too. And then if you remember religion was, one was a Muslim. Remember Muslim traders, the other was Buddhist fishers. So religion was different. So these factors were the ones causing the difference because complement price and income was the same in both cases. So on the basis of that, we can say that the second scenario is much, much, much better. And once you do that, you have been able to do all the possible analysis on regression. Ladies and gentlemen, this is how you tackle regression. You can use these other commands here to get some of the residual analysis, whether the residuals, expected value of the residuals are truly zero. You can use some of these to check those analysis. The Burukutu data set is a wonderful multiple regression data set that you can make a lot of analysis from it. If you like what you have watched, please subscribe to the channel. Please give a comment, because that is one way that you can help me increase the value that I continue to give, ladies and gentlemen. So if you like what you see, if you like what you hear, if you enjoy some of the interpretations you're giving, please subscribe to the channel, send the link to other people, tell them to subscribe, and please just type, I need some explanation on this, or just type, I love the teaching. That will motivate me to give you more. Until then, keep on swimming. Drink deep or taste not from the Pierian spring.